When you have Sentinel data, you use Sentinel data and you try to extract whatever information you can.
This is Andrew Peterson. He started a company called Array Labs with a very simple goal.
Building a near real-time 3D map of the world.
This is my favorite type of conversation. We go deep into the technical engineering to come out on the other side to talk about business models and how you create a sustainable company.
We fly multiple satellites over this scene and they image the same place simultaneously.
This interview might require a bit of prep work though. We start high level and then go pretty deep on radar and satellite images. If you want a more gentle introduction to the topic, a few months ago I made a video explaining at a pretty high level how radar satellite images work. If you got 20 minutes to spare before listening to this conversation and want to brush up on the basics, I recommend you go check it out and come back here after. This is one of those conversations where I don't see the time go by. My mind was blown a couple times, you'll see that, and I just had a lot of fun. This is engineering at its most exciting. This episode is sponsored by OpenCage. If you're building any application or tool that uses location data, at some point you'll probably need to convert place names or addresses into coordinates, or coordinates back into place names. And this is where OpenCage comes in. They offer a worldwide, affordable, forward and reverse geocoding service that's easy to use. OpenCage builds on top of open data sources, which grants much more lenient licensing terms than alternatives like Google, allowing you to store the data as you want and even keep it after you stop being a customer. You can also display it on any map, all at a more affordable price. OpenCage handles all the complexity of dealing with the messiness of the real world and provides a simple-to-use API that allows you to focus on your use case. They have a generous free trial that you can use to get started with no credit card required, and they offer a clear upfront pricing with a cancel at any time, no questions asked policy. To learn more, head over to opencagedata.com. I'll have a link in the show notes. As a side note, OpenCage is also responsible for hosting the GeoMob events as well as the GeoMob podcast, for which I'll also have links in the show notes. Thank you to OpenCage for once again being a sponsor and for their continuous support of the podcast. I like starting these conversations asking the same question every single time. I like asking people how they would describe themselves. So I'm quite curious, how would you describe yourself?
Yeah, the reply I usually give to this answer is that I'm a recovering engineer, which is that I started maybe in one direction, and then rather late in my career kind of switched to this whole founder startup thing. And I think that's something that's really interesting and something that we kind of share is this idea that like maybe there's a difference between engineering and starting a company and kind of what that road and kind of what that journey looks like.
I want to ask you sort of the same question. You've started this company, Array Labs. How would you describe it? Like the way I like to ask this question is you're at Thanksgiving or you're at a family party and people are like, hey, Andrew, what are you up to? Like, what are you doing these days?
Yeah. So it's, I run a satellite company, lucky enough to do that. And then the next question invariably is, satellites, what do they do? And the answer to that question is we're building a near real-time 3D map of the world.
Okay, let's go. Let's peel the layers one at a time. So satellite company building a real-time 3D map of the world. What does that look like? What does that mean? What does the real-time mean? What does the 3D mean?
What does the satellites mean? Yeah, all of it. Yeah.
No, but like the thing about real time is like it's like a high resolution. When people talk about satellite images, it could mean like a week, or it could mean like 6 months. It's like everybody has their own different definition of what real time, of what 3D, of what all these things mean. So I want to get deeper into what does that mean for you, for what you guys are doing.
So I think it kind of starts with kind of the existing satellite imagery space, right? There's a lot of satellite companies out there. There's a lot of EO, Earth observation satellite companies that are collecting data of the planet. And when you kind of look at those images, there's kind of a continuum, a spectrum in terms of maybe quality, right? The resolution of the image, how crisp it looks, and what you're able to discern based on that. And maybe on one side you have companies like Maxar, and maybe on the other side you have companies that are building a little bit smaller satellites. But when you look at all of the images and you kind of look at them, they kind of have this like Frogger sort of view or quality, right? You're looking at this top-down kind of smushed view of the world. When you walk outside, there's like there's startlingly little resemblance to the outside world compared to what you see on a satellite image most times. And usually, what we see when we walk outside are like the walls and the trees and the building, like all these things that have this vertical dimension, this vertical quality to them. And you don't get that in a typical Earth observation, satellite image, the snapshot. And this is really important, right? We have two eyes, in our head for this kind of 3D perspective. That third dimension is very important to us, and being able to capture that somehow is incredibly helpful, right? It's so useful for being able to understand what's going on in the world. And so yeah, that's the 3D part. The other thing, and I guess before we jump into the near real time, we'll talk about what do you need in order to create a 3D image, right? And usually, what you need to create a 3D image is you need multiple perspectives. You need to view that same location from lots of different angles, lots of different sides, to be able to have that three-dimensional quality, to be able to extract that, to be able to capture that. And there's different ways of doing that. They have different like quality levels in terms of what you're able to do. But basically, it involves taking the same picture many, many times of the same location from all different angles and different perspectives. And we do this, right? A lot of satellites will take, to build 3D data, we'll collect the same image, 10, 20, 50 times the same location, but slightly different perspectives each time, and then process all of that together to form a 3D picture. And that works okay. That works pretty well. But there's always a little bit of distortion. There's always a little bit of time that all of these things take to be able to collect. It's hard to schedule all these collects of these different locations. And somehow, if you could get all of these captures at once, and maybe if you could build a system that was designed to have the best quality for being able to capture that, that'd be really interesting. And that's what we're doing here at Array. So as the name says, our Array, it's a little bit telling. What we do is we fly multiple satellites over this scene, over these places on the world, and they image the same place simultaneously from multiple satellites. There's a cluster or a swarm or a distributed system, right, that operates just like one unit that images the same location from all these different perspectives. And that's how we can create these really crisp, much better quality 3D images. And we can capture that in a single pass. And we can capture that, by doing it all at once. And there's also some advantages to kind of going to a distributed system that we can talk a little bit more is in the engineering, weeds a little bit. But by doing that in a single pass, that's how we're able to get that near real-time nature, as opposed to weeks or months or whatever else, the next best alternative would be. And we can do that over much larger areas than are available today from satellites. So that's kind of the genesis of the company. That's the reason the company exists, is to be able to capture this new, much higher quality perspective than we currently can today.
So the idea is to have, rather than just one satellite and take multiple passes. So you can do what, if we were to do this with satellites today, what we can do is you have one satellite that starts looking ahead of where it's going. It's going to look down when it's directly above. And then as it moves away, it's going to look still at the same area. You might get like anywhere from 2 to 3, 4 images at one time. And if you want different angles, you're going to need a different satellite, or the same satellite comes later. What you're saying is,
Yeah.
we're going to send a dozen satellite all at once. I don't know exactly how much. And they're all going to be in this sort of cluster. Like you have these renders of like a circle of
Yeah,
satellites
yeah,
all
yeah,
together.
yeah,
And they're
yeah.
all
That's it.
looking, focusing at the same area. And so you have more angles all at once. And so in a single pass, you can make a 3D model. Is that right?
That's exactly right. That's exactly right.
Okay. So why does it matter that it's near real time?
Yeah, that's a good question, and it kind of goes back to how we capture 3D data today. If you don't have a satellite, right? So we talk a little bit about satellite constructed 3D, and it's a thing. It's a couple $100 million a year industry. But the much larger industry, right? The $1 billion industry that's involved with 3D data is actually from aircraft. And so there are a huge number of companies around the world that actually fly planes. Some of them have laser scanners, they're LiDAR planes. Some of them use photogrammetry, but they fly very close to the ground. They kind of do a lawnmower, collection over a really, not that large of an area, kind of a really small area, but they get really, really crisp 3D data, right? So if you go to Google Earth, and you kind of look at buildings and 3D stuff around there, you'll see these aircraft flying along and or the imagery, that they've collected, and that's what's populating all of these feeds. It's not from satellites. So there's this big industry around 3D data capture, and the quality of the data is awesome. Everything about it is less awesome. So, you have to find. It's not like you call 1-800 lidar for nationwide lidar service, right? You've got to find somebody with a plane near you. You've got to line up a flight to collect 3D data for you, and then you got to have them process that and collect that. They usually put tie-in points in the scene to make sure that everything's really nicely registered. And like this is like this whole thing, and it's like $50,000 per collection, and you get a couple square miles or a couple square kilometers, and like that's your image, and this is what you get. And so it's kind of a most places have not actually been captured in high quality in 3D for this reason, right? It is really expensive to do. And then the places that have been captured, it never gets updated, right? The last thing anybody wants to do after they've gone through all the trouble of scheduling and collecting and sending this plane and doing this thing is to reschedule this plane and pay more money for this thing, right? And so the maps that we have in 3D are either super low quality or non-existent, or they are captured in different formats, right? They're kind of this hodgepodge Frankenstein thing, right? So if you're Apple or you're Google or you're somebody else who wants to have really crisp 3D data for the planet, even if you have a lot of money to go task planes, the act of making sure that all of those planes are calibrated with the same sensor and the data is captured in the same format, and captured in the same way, and the datums and everything else works seamlessly together. Like that's an incredibly difficult challenge and undertaking, and so that and it's also very costly, right? Because you're the sensor, the plane, the thing that is doing the collecting, right? Like that, that's in like the tri-county area. I don't know which tri-county, or maybe it's the tri-state area. I don't know, but it's not global, right? It's not flying to multiple different continents or multiple different countries or deploying planes all these places. Like it would be so much better to amortize the cost of that sensor across the planet Earth as opposed to the tri-county area, right? Like that is kind of a big difference between what you're able to achieve with satellites. And so being able to marry for the first time kind of the quality of a 3D data collect with the convenience and cost effectiveness and timeliness and global reach and consistency of satellite data products, that's what we're here to do, and that's really exciting for us and for our customers to be able to capture this data comprehensively across the entire world, and then be able to provide that to companies that need it. And if they need it, once a month, or they need it once a week, or they need it every day for certain metros and areas, like we can actually do that. With this technology, which is totally crazy and totally impossible to do at that scale with aircraft.
So the reason I ask why is the near real time important is because there are these LiDAR campaigns, they're usually national. So what you're
Yeah,
talking about, you have in the US, you can go and the USGS has an open data program of most of the LiDAR that's been flown around. And it's at about 1 meter in resolution for, I think, about half the country. And it's, yeah, between like 3 and 5 or maybe 10 years old. Um, but for most of the applications that are today, it's terrain. It's we're going to give you an elevation model of how high the mountains are and where the
yeah,
canyons are and the riverbeds and all that. And that doesn't really change at that time frame. The things that do change are what people build on top or what
right.
they cut down, or forests they tend to change, people cut them down. um, so that's really what's going to change. Is that what you're thinking about? Like, we want to get to that high resolution that something like a LiDAR could give you, but so we can also capture all the things that changes on top of the elevation.
If you have this is the thing with like Sentinel data, right? When you have Sentinel data, you use Sentinel data and you try to extract whatever information
Yeah,
you can,
that's
right?
fair.
And it's free and it's great and you use it and like okay, that's really good. If you have 1 meter or 10 meter or what have you, 10-year-old terrain data, well, you use 10-year-old terrain data and you make whatever extractions, and information you can. Um, but it's really interesting, as we've been talking about this, the number of folks who would want to use um, a native 3D product if it existed, right? I mean, things like the canonical
Yeah, yeah, yeah.
SAR radar imaging example, oil containers, and there's a roof, and it goes up and down, and then you measure the global oil supply by measuring all the roofs. Well, you can look at the shadows and make tricky inferences, or you could like measure that it is a roof and it is going up and down with a 3D measurement, right? And so that's a good example. Other 3D, volumetric things are stockpiles of ore or stockpiles of building materials or container stacks or all these things that, look much more comprehensible in 3D than 2D. But even when we talk about things like understanding a car, right? A car sitting on a parking lot. Black car in a black parking lot is really tough to discern whether that is a black car in a black parking lot or if that is a shadow cast by a tree or a nearby object, right? That is really, really tough. And in 3D, it's really, really easy because the shadow does not have any height and a car has height. And so we're not talking about is there a car or not? We're like, which model of car is this? Because we can understand the roof profile and understand what's going on, and we can discern whether that's a car or a tank or anything else that might be in the scene, or just a funny shaped rock. I spent a lot of time in my past life as a radar engineer, a SAR engineer, looking at speckly 2D objects and trying to figure out what the heck I was looking at, right? And it's really, really tricky. And so if you have a three-dimensional perspective, you can do things like colorize the speckly black and white 2D radar image into something that looks better, or you can understand things more completely, a much easier way. And so yeah, it's good for lots of things.
So there's multiple directions I want to go there. One thing that I want to mention, and we'll get to it after, which is you're basically making this bet that there's this whole market, which is like the whole business and finance that I want to get to in a little bit. But we haven't actually addressed it, that this is radar. This is not
This is
some
radar.
optical. You're
Yeah.
not sending um, cameras. And so
Right.
the question that I want to ask is, why not? We talked about 3D and
Yeah.
using angles, and that's kind of how our brain works. We have these two little cameras that have there's slightly offset, and our brain just processes everything using a parallax effect, and that's how we see in 3D. Cameras are really good at that. Like, you can really do that. You can buy elevation models that are made from optical camera satellite images even. So why use radar? Let's nerd out on the tech a little bit before we
Yeah.
talk about
Yeah.
the dollar signs.
I'm here for it. Let's go. Just as a background, right, on radar imaging and kind of how that works. And Max, I know having worked in this technology very closely, you're going to understand, this. But I'll go slow for maybe for the audience. You can use a radar to take images, aerial photographs of a particular scene. There are some advantages of doing that, like you can see through clouds, and you can image at night, and through smoke and rain, and what have you. And the way that that works is you image a particular place with your radar system on board your satellite or on board your aircraft, and you move the antenna as you're looking at that scene. And by moving your antenna, you're able to do this amazing combination of all of these different pulses that you send out. And you can pretend like you have an antenna or a lens that's as long as your flight path, right? You can use the spatial diversity of looking at this scene from multiple different perspectives. And that's actually how we create even the 2D image products that we look at today, right? And the reason we need to do this, radar wavelengths are very long. And so the antenna that you need to use to capture this scene would also be very, very long, too large to fit on a satellite or too large to fit on an aircraft. And so we just move along a baseline and we stitch all of these things together. We create an aperture out of each of these pulses. That's why we synthesize it, right? That's why it's called synthetic aperture radar. So the trick with what we're doing, and the easiest way to understand this, is instead of just relying on this in a single dimension, in the long track dimension, in the path that you're flying, you can do the same thing with two radar systems that are spaced far apart. You can get that same diversity of views, that same diversity of perspective by flying in a different direction, a spatial diversity direction that's created by the individual satellites and their long baselines between them. And so by flying multiple satellites, by flying them far apart, we get an extra baseline. And this second baseline moves us from a 2D image domain into a 3D image domain in kind of its simplest terms. So we get one domain from range, one domain from flying along this cross track and building this aperture in the along track dimension, and then we have a cross track focus that's created by all of these satellites flying over it with that diversity in distance.
So let me interrupt you
And
there. This
yeah,
is
yeah, of
this
course,
is
go for it.
how you can already make elevation models with or like 3D with radar. So there's things like TerraStar X, the SRTM.
Yeah,
Those also
yeah,
had, as far as I can tell, they always have two
absolutely.
antennas. This is just this thing that just completely blows my mind every time. They basically added a retractable boom arm on the Space Shuttle that extended like 300 meters.
Yes.
I don't remember how long it was to get
Yes.
that basically baseline, which is just a offset in distance between those two antennas, so that
Yeah.
in the direction of flight, you have two antennas that are perpendicular to that direction of flight. So you're doing this
Yes.
synthetic antenna, but you're doing it with multiple antennas. So this I think is bistatic imaging, if I remember my
Yeah. Yeah. Both
right.
Tandem X and SRTM are bistatic, which
Right.
means
So it's
there's
two.
two
Right.
antennas. Yeah. Exactly.
But so that's what
Exactly.
we're talking about. I'm kind of like trying to
Yeah.
put the pieces together here. Like we have this synthetic aperture, which is we're creating this synthetic, like artificial size of an antenna in one direction with one satellite. And then perpendicular to that, you're going to add another one. So you can get sort of this parallax effect. So
That
that's
is
where
exactly right.
we're already
Yeah.
doing. And I'm guessing you're saying,
Yeah.
what if we add more?
That's correct. That's correct. That's correct. Because the thing with SRTM data and the thing with Tandem X data is, again, it doesn't work with just one pass, right? In order to actually create crisp models, even 1 meter resolution 3D models, you need to collect the same thing with Tandem X many times. And hopefully nothing's changed in the scene, but the buildings and the mountains and the streams or whatever, they don't change, and so you can do that. Yeah.
You have this spatial baseline and then you have this temporal baseline, which is spatial
Yeah.
baseline is like how far those different antennas are between each other, and then temporal is like how quickly can you just come again before something
Right,
changes.
right. And again, the image quality is like the number of images or the number of image pairs. So there's an interesting trick with bistatic radar, especially if both the if both satellites or both transmitters are transmitting at
Right.
once. So in Tandem X, you have two transmitters. You have transmitter A and you have transmitter B. And when transmitter A transmits, a return comes back to B, and a return also comes back to A. And that's really important because you get two images from transmitter A and receiver A and receiver B all kind of working together. And then if transmitter B is transmitting, well then it gets a capture. It comes back to receiver B or satellite B, which receives it, and it also return comes back to receiver on satellite A, right? And so you get four image pairs with two satellites, right? A to B, B to A, B to B. Those are kind of the four image scores. So you get this kind of like n squared image copies. And four images isn't enough, right? You
Right.
need to repeat that multiple times. You need like for low quality, maybe you need like 10 for like super high quality. I mean, I've seen as many as 100 image pairs be used to create crisp 3D data of these different places. And so if you want to get 100 images, well, you got to go repeat this bistatic collect 25 times in order to get enough diversity, in order to get to build enough confidence in this 3D reconstruction to be able to achieve that. Okay, so how does that change if you have more than bistatic, right? If you're multistatic. Multistatic is just the thing after bistatic, which is okay, you have more than two satellites, right? How does that work? Well, if you have three satellites, you get nine image pairs. If you have
I
four satellites, you
see.
get 16. If you have five, you get 25, right? And so very quickly, like if you have 10 satellites, well, you get 100 image pairs in a single pass. Oh, with 100 image pairs, you can now form crisp 3D in a single pass. That's really exciting, right? That's really really good. Um, with four satellites, you have 16 image pairs, right? You can build a medium low quality 3D scene with that in a single pass. Okay, cool. Um, and how we're doing it, I'll kind of nerd out a little bit. We're able to do that in strip map mode, right? We're able to just fly over top of the scene and continuously collect this 3D content with all of these satellites in a single pass over a very long distance. And that's what gives us the right to say near real time, right? Or
Right.
we
I
can
see.
cover lots of area quickly, right? Because you can actually do this, as a wide area
So
collection.
yeah, we skipped over a big trade-off in most, like every imaging thing, which is this trade-off between resolution and um, coverage swath. Um, so if you have an optical satellite, you decide that the moment you build the satellite. How big is the lens? How far is it going to be? As far as I can tell, I don't think there's any satellites that can like change their aperture in air.
Yeah,
But with the
correct.
radar, you get this really weird property, which is that you can kind of decide what you want, and so that's what you're referring to these different modes. You have spotlight. You imagine a spotlight. If we're going to concentrate everything over an area, we're going to get the highest resolution, but we're going to get a tiny little coverage. That's the equivalent of I'm going to use a giant zoom lens. I'm going to see something
Yeah,
very, very
yeah,
high, a
yeah.
lot of details, but in a very narrow area. And what you said, strip map is sort of a wider lens. To use that analogy of photography, you're having this wider lens, but at the expense of accuracy. And so what I'm hearing is you're saying we can have this sort of wider area and still get 3D models, which is interesting because then you can basically sort of take the whole area as you go. You don't need to do this
That's
trade
right.
off of, as we're doing a pass, as our satellite is orbiting, which area are we going to look at? And then not look at everything else. What I'm hearing you say is you can make the we I want to get into like what quality are we talking about, but whatever quality you deem
Yeah,
good enough, you can do that for
yeah.
the whole area as you go.
I'll tag in a little bit more detail around the difference between Spotlight and Strip Map, right? We talk about when we talk about SAR, we talk about this idea that the satellite moves, or the radar antenna moves, and we collect images pointing at the same location as that satellite moves. And the longer we keep doing that, The longer we keep something in view, the higher the quality the resulting image is going to be. Okay, that's cool. That's point one. Also, in order to do this, so we need two things to build a good SAR image. One is we need to keep looking at it long enough. The second thing we need is we need to look at it with enough power, right? We need to send enough power down to the ground and have it bounce back. And we need to capture enough of it to have good signal to noise ratio, right? We typically measure this as sigma naught or something like that, which is a denote of like the contrast level of the image. If you don't have enough signal to noise ratio, everything looks really washed out. There's not enough contrast between your sharp bright points and your deep shadows, right? You don't get that contrast level. So you need both. You need the long enough imaging baseline, and you need enough power that's associated with that long baseline to be able to resolve it into something that looks nice and crisp. So and high contrast. So there are two ways that we sort of can do this. One is spotlight mode, where we stare at a particular spot as we go by, as we go whizzing by, and then we can get like the ultimate, right? We get to choose. We get to choose how long we stare at this scene, and so we can build a low resolution image. If we only stare a little bit, we can build a very high resolution scene. If we stare for a long time, this is this trade-off that we're able to achieve. Or you can do the simpler way, the wide area way, which is we're going to point the satellite at a fixed angle, and we're just going to image whatever comes scrolling by, right? And so we just point the satellite, we send out all the pulses, we just keep going and keep cranking as we're looking down at a particular scene, and whatever baseline we happen to fly when objects come into view of our beam and kind of leave at the trailing edge. Like they come in from the leading edge of the beam, they depart from the trailing edge of the beam, and however long they were in view as we scrolled by is the resolution that we're able to achieve with that system. Okay, now the size of the satellite, the size of the antenna, has a big effect on the resulting image quality, and has a big part to play in kind of trading off this balance between what you're able to achieve from a signal to noise perspective and what you're able to achieve from a resolution perspective, right? If you have a really big antenna, well, hey, you've got great SNR, right? You can image something
Signal
with
to
very
noise
little
ratio.
power, right? That signal to noise ratio. You have a lot of contrast. You don't need much power to form that image. That's really, really great. But the problem with the really big antenna on your satellite is that the beam that you cast on the ground is comparatively narrow, right? It's quite fine. It's comparatively narrow, and so as you fly over this scene, the distance between the leading edge and the trailing edge is actually not that long, which means that the baseline that you create with the image is also not that long, which means the resulting quality of that image is also not that high. So paradoxically, your signal to noise ratio wants you to build the largest antenna you can possibly build. Your resolution in StripMap wants you to build the smallest antenna you can possibly build, because small antennas cast big beams, which means the distance between the leading edge and trailing edge of the scene is very long, which means your length of your aperture is also very long, which gives you really crisp resolution. And so you're stuck. You're like, okay, well, I want a big satellite from one case and I want a little satellite in the other case. Gee, I wonder if there's a way out of this bind. Is there a way that I can have my signal to noise ratio and my power efficiency and my big antenna and my big area that will allow me to get my contrast for lower power? And can I also have a really long beam so I can get my good quality? How would one achieve this? And it turns out you can fly multiple satellites at the same time and have them work together. And that's what we're doing. And that's really the secret to being able to provide high quality 3D data over wide areas. Because the more satellites you have that are operating in conjunction with each other, the more antenna area you have, which increases your contrast. But each of them have small antennas, so they cast big beams, which gives you the long baseline that you need to resolve it clearly. And so that's what we're doing. And that's why it works so well. Multiple satellites flying in formation gives you 3D, and it's also hyper efficient. It allows you to have all of the benefits with a much, much larger satellite without having to build a large satellite, without having to fly a giant gossamer structure that unfolds majestically at great expense and great difficulty. No, you build small antennas, which are easy to manufacture, and small satellites, which are easier to manufacture. And then you fly a bunch of them together. And when you do that, you can have your cake and eat it too. You can have really long baselines. You can have really good quality, really good diversity in view from the spatial perspective, really long baselines in strip map mode, which allows you to cover wide areas. And it's super efficient from a collection perspective.
Man, physics is weird sometimes.
That's right.
I'm just
That's right.
I'm just like taking that in. Okay, and then like that's what you talked about, like this distributed system. If you lose a satellite, like yeah, it's a big deal, but like it's okay. Like
Right.
you can um still get, even if you say you target we're gonna have 10 images, and like if you know the number of images that you get is this, you know, a square function of the number of satellites, like losing one is actually, you know, you go down very quickly. But if you say, you know, as long as we have, you said 16, then we can lose quite a few satellites.
Yeah.
um,
Yeah.
so I see that
Yeah.
as being like an additional benefit. The
That's right.
low
That's
power
right.
means that, you know, the weight is also smaller. I'm guessing that scales also much faster. Like you, for people who are just listening, there's some like what looks like two U satellite CubeSats behind you.
Yeah.
So it's like a 20 by 10 by 10.
I'll show you the other thing over
Sure.
my left shoulder.
So for people listening while Andrew is doing that, he's pointing what I think is a solar panel that's the size of
Yes.
like a A5 piece of paper, something like that, A6.
Yeah. So this is a satellite that goes into a cluster of 50.
Okay.
This is the radar panel of this
Oh,
satellite,
it's the radar.
and
Okay.
and the opposite side is the solar panel.
Oh, that's cool. That's
Right.
clever.
And so there's a payload electronics bay which houses some processors and some batteries. But this is the ultimate low cost satellite that you can build. So this is a flat panel. It's called a microstrip antenna, which is an antenna that's built using printed circuit boards, and we can build this antenna for very little cost. It's very similar to like 5G base station technology that's being deployed around the world, and we attach it to compute CubeSat components, and then we fly it. And this is what you can use with a bunch of these satellites flying in formation, flying together.
Right. And so does this looks like there's no moving parts. This is like just one block. Is that correct?
Yeah, that's exactly right. So there's reaction wheels inside it, which are used for pointing, but there's no flip outs, there's no fold outs, there's no complicated deployment systems. It's a really efficient design that allows us to have very low cost individual satellites, and then gang many of them together to build one gigantic satellite.
It has a bit of a Starlink vibe, even in
Right,
sort of
right, right, right.
the shape. It's very flat. It's very. I do recommend, like, if
Yes,
people are just looking, just listening, like I'll try to have some links where people can go see what this looks like, because
sure.
it is interesting. This is one of the things I remember from my mechanical engineering time is like you want to bring the number of moving parts down to zero, if you can,
Yes, yes.
especially when you send things to space.
Yes,
So
where
this is
there's no repair. Yeah.
Yeah, exactly. Okay, so you said, so this is the antenna, this is the solar panel. What about do you need anything else to sort of send data down? You need, you know, a bit of onboarding process to do the signal processing, but like
So the same antenna we use for radar and for downlink. So we actually have technology that's good enough today to be able to have a dual band antenna and a dual band RF chain. So we can actually communicate down to the ground with this, which means that all of the data that we collect we can send down to the ground very efficiently, and at very high data rates. And yeah, it's a pretty self-contained, low-cost unit that we're able to do that unlocks, yeah, incredibly high quality 3D over these distances. Yeah. So you asked what the quality was of the image. It's 20 centimeter resolution imagery in strip map
Damn.
over very wide areas and also in 3D.
So that's like vertical accuracy as well. Like height is
So
also.
so vertical accuracy is even higher than 20 centimeter. It's 5 centimeter vertical accuracy and 20
Wow.
centimeter horizontal accuracy. Yeah.
So that means you can see. I'm trying to think like what does that mean? So the reason why I'm talking about like vertical accuracy is because like that really matters because you could imagine that this is something that doesn't come up when you're talking about just satellite images. There's not really. You
Right.
might talk about signal to noise and like the quality of the pixels, but if you take satellite images, it's a flat image. So there's really just
Yeah.
how what's the resolution of those, and then you might talk about like the signal to noise ratio. In radar you might talk about speckle, but as soon as someone starts wondering about elevation and that um, third dimension, like you start having another metric that you want to care about, which is like, okay, you can give me small area if I project it down, but if I go up and down, how accurate are you? And so you're saying 5 centimeter for that, which is like you can see like tiles in a roof. If they're big tiles, like you can see the staircase effect. That's wild.
Yeah, you can do, and then you can do like object ID. This is a radar system. This is a rocket launcher, you know, surface air missile battery or something for military use cases. You can tell, you know, this ore pile or this stack of containers or this like whatever you want to view looks better in 3D. As a 2D radar engineer for a very long time, I can attest that 3D data looks so much better than SAR. Right? SAR is so hard to be able to discern anything from. And so if you can move from 2D, one of the things that makes SAR difficult is something you mentioned that you said kind of like that speckle and that mono illumination, right? If you ever want to know what a SAR image looks like, you know, viewers at home, go into a very dark room and hold a flashlight right at your eye level. That's what things look like. It just reflects in the weirdest way. You get this bounce back effect, but you don't get any diffuse lighting. It's very harsh and it's very difficult, even with your eyes, to understand whatever it is that you're looking at. And then you try to do that of something you've never seen before in radar wavelengths, and it's like, oh my gosh, this is really tough. And so by having multiple illumination sources from each satellite, we also get much softer lighting. I know it sounds crazy, but you know, much softer lighting in the scene is so much nicer to be able to illuminate whatever it is that you're looking at and have a more balanced view of whatever the objects are, right? It's like a speckle reduction technique. And so, yeah, you have 3D and it's reduced speckle and you know, it's crisp, right? It's really high quality. 20 centimeter SAR data is really hard to come by, and 20 centimeter SAR data across very wide areas, well, that's unheard of, right? That's not something that people do or can do, right? 20 centimeter comes from a spotlight mode. It happens. It's a 4 kilometer by 4 kilometer image, right? Or 2.5 by 2.5 mile image. That's what you get. That's what you can have right now. And now we're like, no. Actually, swath width is 25 kilometers, right? Swath width is you know 18 miles, right? That's and it's continuous, right? For a very long time, you can have this, right? As we fly over the scene, right? You know, for another 100 or 200 or 300 miles, right? You can get this collect.
Yeah, I'm sort of like just internalizing all these things. Like the main one of the benefits of like you being able to do this sort of as the satellite goes is you don't need the individual satellite to move. You don't need the antenna to move.
Yep,
Um,
super simple.
you can so your lifetime of satellite goes up because even if you have reaction wheels, like they can saturate and then you need fuel to like unload them, but
Yep,
if you don't move them
yep,
very often you don't need all of that.
right.
I'm just like going through the sort of second order effects of like what happens when
Yeah.
you do that. And you said like,
Yeah.
so you have like 25-kilometer swath?
Yeah, that's correct. That's correct.
Okay.
That's
Yeah.
correct.
So you can cover like a whole area. You can do a city in
Yeah,
one pass.
correct. You can. You can. And you can keep going. You can go. And then the next satellite comes, next group of satellites comes in behind it, or the satellite comes in later. And you can start building. And there's even higher swath modes that we can operate as
I'm
well.
sure. Yeah. Yeah. This
That we're
is, yeah.
talking about. So and continue to keep our 20 centimeter quality. So yeah, there's some really cool use cases with this. There's a really cool use case with this technology. And it shouldn't like shock anybody. I don't think, right? I mean, it's like if you look around you and you kind of think about the world of computing, there's this famous story in 2005. This great cry went up. Moore's law is dead. Like we're never going to get faster processors than we have right now, because what had been happening for the last, I don't know, 20, 30, 40 years before that is clock speeds would increase, right? The speed that the crop processor would work was going faster and faster and faster. And so it would take less time to compute whatever it was trying to do, right? And so it would go up like, it would like double, every couple of years or whatever it was. And then we got to like 1 or 2 gigahertz and we're like, oh, that's it. That's it. The clock speed isn't going to go up anymore. Right. And even today, right. 20 years later, clock speeds are now like maybe 5, right? 4, 5. We hit this wall. And so everybody in 2005 was like, what are we going to do? Moore's law is dead. There's no more increase in compute speed. All the computers will run Windows XP from now until the end of time, right? And everybody's like, okay, well, 2006 comes around, Intel releases the dual core processor. And now, I don't know, my laptop probably has 30 cores in it or 16 cores or something stupid, right? And like, that's what we did. We went laterally, right? I can't give you a 50 gigahertz processor because it will melt, right? Or it needs to be like liquid nitrogen cooled or something, right? It's crazy. I can't give you 50 gigahertz. I can't give you 500 gigahertz, but I can put 20 cores or 30 cores on one piece of silicon for almost the same price as we can get one, right? And here you go. Now we can continue with the speed of compute, right? And GPUs are just like this, but more, right? GPUs have thousands of processor cores on one piece of silicon, and each processor is really puny and does not do very much, but you put it together with thousands of its friends, and all of a sudden you've got the most efficient compute architecture known to mankind, right? Like this is what we do, right? And and this was part of like my story. Like I was a radar engineer, and we were building radar systems. And I remember my boss trying to convince him that what we really needed to do was buy this $4,000 NVIDIA, GPU graphics card that had just come out on the scene. I can still remember it's the NVIDIA K20 graphics card, and it was very expensive. And I thought, but the workload we were doing was perfect for GPU compute. And I remember telling like, this is going to save us so much time. We can do all this algorithm development. It's way more efficient. And so we did that. It made everything so much faster. And then we actually started shipping radars with GPUs on board to do really efficient compute and processing of the image formation workloads that we had. And that was a big moment for me because that is what seeded the idea for Array Labs. Because I knew a couple things. I knew that computers were not going to get slower, right? Processing was not going to get more expensive as time goes on, right? GPUs are going to keep getting faster. Processing speeds are going to keep getting higher data rates and higher processing rates for lower amounts of money. And that will probably mean that there are different opportunities to do things that are more computationally intensive than what we have today, that we've always wanted to do, but will be available tomorrow. And what is that going to look like? Well, what's more computationally intensive than one radar operating by itself? Well, it's multiple radars operating together, right? Okay, cool. If we can do that cost effectively, what else do you need in order to make that happen? We also need low-cost satellites, right? You need commodity, reaction wheels or commodity CubeSat components or commodity things, launch prices, but most importantly, the individual unit cost per satellite has to come down. Oh, hey, look, that's happening too. Well, you also need really low cost RF technology, right? Well, cell phones have made massive, massive improvements in our ability to build things and operate things that are really good, RF performance, really high quality, again, really low cost. Okay, so if you combine all these things, you're like, oh, this is how we get to Array Labs, and this is what kind of underpins the why now explanation for all of this performance. It kind of echoes kind of the GPU conversation. It's a distributed system. Multiple things operating together can oftentimes be much, much better than one great big thing, right? And so that's kind of where we are.
I like that analogy. It makes a lot of sense. Again, I'm sort of thinking through as I go. The This is also not some crazy setup that you need to do once you're in space. Like they're all pretty close together, so like you can just send 50 at a time or like 20 on the same launch, and then
Absolutely.
they are pretty packed together. So on the processing side, like one of the things I remember of my time like working at a I worked at ISI, um, at a radar company, radar imaging company, is like there's a lot of processing. Like you, even with like one satellite, you send a ridiculous amount of pulses down, and you receive like an even more stupid amount of data. And so the you receive all of that, and then you sort of process it into whatever image you want. Like you can, and we're still discovering new ways to do that, which is sort of a different way to do imaging than a camera, where you just have a sensor and that's how much light
Right.
there was. How much work do you guys have to do to figure out how to process all of that as well? Is that also, so biostatic, I'm guessing, solved problem plus or minus some work, but how much work do you need to figure out like what happens when there's 10 satellite? Does the sort of software processing part of the work also get that much more complicated, or is it just scale the compute?
It's not to trivialize it, but it's scale and compute. Um, there's a particular algorithm called the back projection algorithm. I don't know if you spent time kind of like deep in the weeds of image formation
It
theory,
rings
but
a
is this
bell, but
something?
I
Yeah,
don't know what it
yeah.
actually is.
So there's actually a story, right? SAR was created in like the 1960s, and there was this algorithm that they figured out that could be used to form absolutely pristine imagery. It's called back projection, and what it involves, it involves making a matched filter for every pixel in the image and processing each pulse kind of like lovingly hand processed for every pixel that you wanted to see in the scene. And if you could do that, then you'd have just a perfect image, and it would be super well focused, and it would be awesome. And then the next thing they said is, this is a stupid algorithm. No one will ever use it because computers will never be fast enough to ever process data like this. This is completely impossible. And so they made like 27 simplifying assumptions
Yeah.
that each assumption was made, and it screwed up the image quality, but it made the computing job easier. And so then you're left with, crappy imagery from the 1960s because that's all that they could do with the processors and the computers that they had. And then every few years, somebody would say, hey, these computers are fast enough. We can remove this simplifying assumption. And I was there in 2011, 2013 timeframe when the last simplifying assumption was lifted, and we could do back projection with a GPU on board a radar, and it was great. And then the next thing happened, which was, not only can we do back projection on this radar, we can do back projection at video frame rates. And so we had a product called Video SAR, which could turn a radar imaging system into an actual video camera and could keep up with all of the processing loads and demands that required. And that's when I said, okay, come on, right? Like, this is unfair. We're moving into this totally different realm that is led by this algorithm back projection that we can now do at silly speeds. Well, guess what we're using to process all of the data from all these different satellites into a particular scene? It's back projection. That's what we're using, and that's only possible again, but it's a scale and compute problem, right? It would take a really, really, really long time to process this data. And it's not exactly like falling off a log cheap either, right?
Yeah,
If
yeah,
you
yeah.
look at kind of our cost of goods sold for the satellite at high production rates, like if the satellites are collecting as much data as they are capable of collecting every single day, like 1/3 the cost of the image is amortized hardware. 2/3 of the cost is downlink and AWS processing, right? It's kind of staggering in terms of what you need to do in order to get this done. But it's actually a solvable problem now, right? And of course, as time goes on, cost of compute will get lower, cost of satellites will get lower too. So cost of imagery is going to get cheaper over time as well. But it's a really efficient way to do this. But yeah, thank goodness for the cloud providers and commodity compute, because otherwise this would take a long time to process this.
So that answers my other question that we had earlier about like what is near real time. It's basically whatever the downlink and processing time is. So it's probably like can be anywhere from like a few minutes to like probably still a day. Like it's really limited by the like funnily enough, I from what I remember, like AWS also owns most of the downlinking stations, which are over just a few. But that's the sort of high latency aspect now. Is
Yeah, yeah,
your
yeah.
satellites collected all this data, but there's no antenna in view to be able to send it down. So you just need to wait
Correct.
until it gets over there.
Correct.
But
Correct. Correct.
so
Correct.
does
Correct.
everybody else
Right. Right.
until
Right. Right.
like we had a better solution, but that's sort of outside your control. So a lot of what we've talked about is not quite there yet. We don't have like you don't have that ring of satellites going on around there. What does Array Lab look like today, and what is sort of the plan for the next few years?
Yeah, we have 15 people, and we're working in Palo Alto, and we've launched 2 test satellites, a few weeks ago, and then we're gearing up to build our first radar satellite, which we're going to be launching next year. And then after that, if everything works as well as we expect with that radar satellite, then we're going to launch 4 radar satellites together. And 4 satellites will collect, as we've discussed, 16
16
image pairs,
images.
right? Which is good for medium quality 3D data, like 1 meter quality data will be able to be collected from that. And that will be capable of collecting enough 3D data to capture the whole world every quarter. That is our next thing, and we have customers who are super excited and super eager to get their hands on a comprehensive 3D map of the world, updated every quarter at 1 meter. And then as we go, we will launch additional clusters of satellites to bring that revisit rate down, and then also to increase the quality of the imagery that we're able to collect. And we'll focus that quality on things that are changing rapidly to start, the cities or high interest areas of the world. And then we'll gradually scale that out to being able to capture the rest of the world as well. And so this is the thing that we're building.
I've been kind of wanting to talk a little bit about the money aspect as well. Sort of how you
Sure.
fund all of that, how you get people to buy it. And there's a lot of different angles in here. We're going to spend a bit of time talking on this.
Yeah.
The
Yeah. Yeah. Yeah.
the first one is okay, we've spent like an hour nerding out on cool tech, which is amazing and it's awesome, but
Right.
you need people who don't care and just see value.
Right. 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 Right.
Is there, of course, you're probably a bit biased, but do you see that being a thing? So, specifically, I want to say earlier in that conversation, you said, if all you have is Sentinel, people will use Sentinel. So now you're making a bet that there are there's enough people that are willing, that have use cases or new use cases that are going to come up that are going to pay multiple times back what you're putting out in here. And specifically well, not specifically, but that's sort of what a lot of the more, let's call them traditional or just imaging vendors are also doing, like the planets of the world, and then the um, boring 2D radar images we talked about, but like all this whole other Earth observation industry, basically. Um, and there's a huge giant asterisk as to, is this whole industry commercially viable? I can bring the very easy example of like pull up stock value of whatever the 4 or 5 publicly traded companies are. They're not doing very well. Some of them might get delisted soon. So what is giving you that confidence that like we're having a more specialized product, which is like 3D? It's not even just the images, but there's going to be enough that we can make that back, and it's going to be a profitable business.
Yeah, I think that's a great question, and a very important one to answer for any entrepreneur or would be founder or anything like that to kind of get their head wrapped around before they quit their day job and go start a company. So yeah, it's a great question. I think as you look across the spectrum or of Earth observation satellite companies, we'll start there, right? And some of the big ones you've mentioned, Planet and the other 2D star companies and other folks. Black Sky is another one,
Mm-hmm.
but kind of what you see, and it's really super clear to see this in sort of the optical landscape, is the companies that have the largest satellites with the largest cameras that can take the highest quality images are the ones that are doing the best, right? Um, Planet Dove data is amazing and it's wonderful, but it's 3 meter resolution. And at 10 foot per pixel, it is relatively difficult to see what is going on in any location, right? A car is like a pixel and a half. This is really tricky. Whereas if you're talking about Legion data, that is 1 foot resolution, well, you can see a whole lot more. And people are not super interested in going to standard def TV as opposed to high def TV because standard def costs less. This is not a human behavior pattern that we see a lot, right? If you can get a crisp image of what you're seeing, right? Once you go to 4K, you're not like shopping deals on an HD TV, right? You want to go to the highest quality image you can possibly see of the world. That is what makes the market, right? And so this is why Maxar does $1 billion in revenue, and Planet and Black Sky, are a tenth of that, right? Because they're lower quality
Interesting.
systems, right? At least until Pelican launches. In the case
But
of
that's the
Planet,
direction the
right?
company is going
That's
as
the
well.
direction they're
Planet
going,
is
right?
going
Yeah,
towards higher resolution,
right,
more
right,
bands, hyperspectral as well. But I see your point. Okay.
right, right. Now, from our perspective, what is higher quality than? Sorry, I'll mention one more a company in this space, which is Albedo, which is kind of a close cousin of ours who both went through Y Combinator. They went through about 18 months before us. So they're, we talk a lot about what they're doing, but they're building 10 centimeter quality optical imagery from their VLEO satellites. And so, and they've raised a huge amount of money, and they're super successful in that. And what they're betting on is not necessarily pointing at all the other Earth observation companies and saying, look, we can do this better, and therefore we're going to eat their lunch. They're actually looking to the airborne companies, right? Because remember that people flying planes and collecting data with planes is larger than people realize, right? It's actually larger than a lot of satellite collections. And this data is being fed into all sorts of commercial industries all around the country, right? Whether this is insurance analytics or infrastructure monitoring or construction or any number of augmented reality, self-driving cars, like people fly planes all the time to go collect data. And a lot of what they collect is 2D, and they collect it at, 5-10 centimeter resolution. And a lot of what they collect is 3D. It's LiDAR data. It's 3D photogrammetric data. And so if we're looking at what our market cap is and we say, hey, we have a drop-in replacement for airborne LiDAR and it's at a fraction of the cost, and it can be collected in a fraction of the time. Do you want this? It's not a hard sell, right? It's when can I have it? Give it to me. I need it. Like this is a thing that we absolutely desperately need, right? And this is, billion-dollar industry of people flying planes and collecting data that we're stepping into. That there has no direct, comparable to high quality 3D data, conveniently accessible. And then you put on the other things, right? It's available through clouds. We can image at night. We can image reliably and consistently, and we can plan all of the things with a SAR system that you can't even get with an optical system. You're like, okay, well, we'll do this then, and so this is kind of what we see, right? The the highest quality data set is it's good spatial, it's good 2D data, but the highest quality is actually 3D because you learn the most from that, right? You answer the most questions by having that crisp three-dimensional perspective, the two eyes in your head perspective, right? That's the 4K TV or the ultra high def TV, signal in this analogy, right? It's being able to, and the analogy falls down a little bit because 3D TV might be like a thing, like,
Yeah.
well, nobody like really uses this, like, okay, like I get it, that makes sense. But for computers and for people who are trying to make money by observing the world and understand what's going on there, or people who are charged with national security issues or other things, being able to discern what is on the ground is something that is actually not done as often by humans. It's actually done a lot more by computers. And having good inference and signal that you can plug into a computer and say, this is a 3D image of this thing. This is a volumetric structure of this thing. It's this shape. It's this size. It's this pattern. That is the thing that we're looking at and saying, yeah, this is something that's going to be really valuable for all of these different applications, especially when you can collect so much of it so quickly at such high quality.
Yeah, again, I'm sort of running through the second order effects through my head. One thing I can see being like you mentioned, you get the see-through clouds at night. So you basically get uninterrupted data collection. You don't have, just when the sun is out and when there's no clouds. That's another benefit of getting the radar imagery. But you also, in a way, I you don't have this high barrier of entry that SAR imagery has. Like radar imagery is amazing, but I've this is sort of a notice that I've taken on this whole industry is that the uptick in use of radar has this weird problem that isn't necessarily an engineering one or a cost one, which is just it's unintuitive. And like that's a very
Yes.
hard barrier to entry, but that's hard to measure because if you want the sorts of volume, you basically want your sort of random student with a laptop to just start tinkering and start a business. They don't really know how to use this data. So like it's this really
Yeah.
complicated thing where like it's a high barrier to entry for the people outside the box to come in the box and have those outside the
Yeah.
box
Yeah. Yeah.
ideas.
Yeah.
And
Yeah. 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 Yeah.
you
Yeah.
don't have that because it's a derived product as well. Like you actually don't really care how it was made.
But a really good analogy, yeah, is X-rays, right? Like X-rays and MRIs, right? If you are a doctor and you are trained to use an X-ray, boy, can an X-ray tell you so much because you're an expert. You know what you're looking at when you see this thing. When I look at that thing, I'm like, I think I see a bone, right? Like, I am not sure what is going on in this image. This is not intuitive to me. This is something that's very complicated. But if I look at a slice from an MRI machine, you don't have to unpack all of the layers of that swath through the human body and try to figure out, is that an overlay of this organ on top of that organ and this is normal or this is not or whatever. Like, oh, actually everything in this slice I understand this is the white part, this is the gray part, this is the black part. These are what these things are. And now I can understand this just by looking at it. I don't have to be an expert in order to look at this. And the same thing is true for 3D point cloud data, which is what we're able to collect. It looks just like this. It looks like slices from an MRI machine, or we can take the top surface as well. We could have a tessellated surface that people can use and people can play with. And it's super easy. It's super intuitive. It's way better than if you were outside of the box. It's way easier to get inside the box and be able to understand what this is looking at. And even for people inside the box, it's a drop in replacement for something they already use, right? People know what to do with 3D point clouds and LiDAR data from planes because they fly them all the time. And so you're not actually trying to get our largest customers to change their behavior. They're super sophisticated, they know what this is, but for the first time, that thing that they know and love can now come to them faster and cheaper and more conveniently in places that, like, you cannot send a plane. Like this place here in a far flung corner of the world, you can't get this data. And so not only are we faster, cheaper, more convenient, whatever it is, we're also the only available solution for these different places. And that's really exciting as well.
Again, I'm processing this in real time. I'm sorry, I'm still single core. I haven't managed to get multi-core thinking going on.
That's right. That's right. That's all good.
But yeah, thinking about what you mentioned about the different use cases, I've thought about this even for the imaging. It's like if there's sort of this barrier or these steps or different thresholds in terms of the resolution and the use cases that it unlocks. So what it means is if you are at a geosynchronous orbit and your resolution is 1 kilometer, there's really one thing you can do, which is where's the storm going? If you drop down to hyperspectral and you have like 100 meters, now you can sort of get like this whole vegetation area, how is it doing roughly? And then you drop to like 10 meters. And so like at Sentinel, like you start having hundreds of applications, and by the time you're at like sub-meter, you've probably got thousands or tens of thousands of different things you can do. And by the time you get to like, you can point your phone at something and like it can tell you like the shape and the structure of everything. Like it's like the resolution that you have also has an exponential in terms of the use cases that you have. It's not really linear. Like if you double the resolution,
Yeah.
you get to do 2 more things. It's probably not exactly that, and it's different. But I think I see your point on like betting on the high res. But the reason I bring this up is like, why stop there? Why not say we're gonna send like 100 satellites? Like, how did you decide it's gonna be 10, and we're gonna sort of spec it for 20 centimeter and 5 vertical?
So there are some constraints in the industry, like how many satellites fit inside a Rocket Lab Electron
Oh,
fairing, or how many satellites
right.
you can deploy from a quarter plate or a half plate from a SpaceX rideshare mission, and that ends up sizing the number of satellites we deploy. But NVIDIA does not make one GPU, right? It's like, here's the GPU size, here's what you get. This is good for everybody. You could have this one thing. They make different makes and models, they do different things. And so just like NVIDIA, sure, that like this was really good for video processing. This architecture is really good for 3D imaging. And that's where you start. Well, maybe that's not the only thing that this thing does, right? Does this thing do maritime surveillance? Does this thing do space situational awareness or space domain awareness? Can you image other satellites with this? Can you image airplanes with this, right? Is this an airborne early warning aircraft replacement, right? Well, is a GPU for graphics and video games? Is that the only thing it does, or is it good for maybe numerical compute and the things that I was using it for radar processing, or is it good for AI/ML and the huge industry that has launched? Well, it's the most efficient compute architecture for all of these things for a reason. And so you start with one, and then you move to the adjacent application, and then you move to another adjacent application. And so in our case, yeah, this is really good for 3D data, and that is absolutely not the only thing that we are going to use this thing for. We are going to launch more satellites and more configurations and more things as we get further along in the realm of global domain awareness, right? What is going on in all these different places and all these different times? Because this is the most efficient way to be able to solve those questions as well, right? A lot of planes out there with radar systems. Um, a lot of money, right, is spent in this, right? I think the latest airborne early warning radar system that the United States has bought is two planes cost $2.5 billion, right, to get started, right? And it's not obvious that if you send a giant plane with a giant radar that's broadcasting with super high power into a contested environment, that plane is going to come back out again, right? Like it is also not like super understandable, right? And so like, okay, well, if you only had a distributed system that could operate in a resilient fashion, right? There's no single point target, right? Because you say, okay, well, like we're going to do the radar thing from space. We're going to build a giant radar satellite, and it's going to be great, and it's going to be an AWACS replacement. Like, cool, you're going to do that, and then somebody will blow that up too, right? Because like things in space are not super safe anymore. So wow, if there was only this architecture, it was hard to jam, it was hard to attack, that you could launch for relatively low costs, and you could put up there that had really long baselines between the satellites. Turns out that that really big antenna we can create by the spatial diversity can answer all sorts of really interesting questions. So I'll leave that there for future TAM
No, but
expansion.
I like that you guys are starting with this is the use case that we're going after. Like I think it's the sort of problem that you have when you are someone like an Nvidia, or you are this sort of bedrock technology or something. Like you could do everything, and then that means that you end up doing nothing really well. And so in a way, I feel like that's pretty clever because it gives you guys a focus, and it allows you to develop the technology, get some reps in, um, and that's probably where the market is willing to give you some money. Like go in convincing, like you don't need another AWACS. Like that's a whole other conversation. Like
Yeah. No, exactly. Like, wait, you said what? Like, come on. No, you're exactly right. And that incremental progress for this incremental market, or even if it's incremental engineering, right? We try to be really disciplined with this as well, right? This is why we're building one radar system, and it's a bigger radar system. It doesn't fit in the same form factor as what you see behind me, right? It's a bit larger, it's a bit less sophisticated, it's a bit less sexy, but we can concentrate on building the payload, and we can build the radar system, and we can build everything that works well together in concert with each other. And then we don't do 50, we do 4. And hey, even that is a really great market, right? We have customers lining up for worldwide 1 meter resolution data. They're super excited when that comes online. And we can keep that to be our focus. Like we can be disciplined, we build one thing first, then we can build something else, and then we can go from there into the dozens of satellites operating together and all the amazing things that that does. But we start by doing the thing that the market really wants us to do from a customer perspective, right? One of the things we did. So you're talking about this journey between being an engineer and being a founder. We got into Y Combinator as I kind of mentioned before. And for those of you who don't know, YC is like kind of a 12-week period, and you meet with some of the greatest minds in startupdom, and they kind of give you some advice about what you should be doing. And then at the end of that, then there's a fundraising event, and you can meet with lots of investors. You can talk to them and see if they'd like to invest money in your company. It's this event called Demo Day, right? Demo Day, you unveil, you meet all these investors. It's really good, right? And so when I started Y Combinator, my co-founder and I were accepted. We're like, oh, I've got this great idea. We're going to build this 3D radar test range, which is going to prove to everyone in the world that 3D data is possible to collect and process, and it's going to be great. And we're gonna do it, and then we'll show that off at Demo Day, and that'll be amazing. And all of our advisors at YC were like, "This is a stupid idea. Do not do this." Instead, my co-founder sent out 400 cold emails and we had meetings with 60 companies in 6 weeks. And from that, we had $100 million in soft commits and LOIs by the time demo day came around. And that was a much better idea, right? Is to socialize the idea with customers and make sure that they want the thing that you're trying to build, and to be able to articulate that to an investor in a coherent way. And that's what we did. And that was the right answer, right? And so kind of trying to balance this, the engineer half of my brain, or the recovering engineer half of my brain, with the customer side, which is where our focus is right now, and keeping them kind of in sync and keeping them both moving along as time goes on. That's been kind of an interesting balance to try to strike. Because it wasn't always like this, right? I think we alluded to this at the beginning of the call, but Max, you and I met in I don't know, maybe if you want to tell the story about how we showed
Sure.
up and
I
first
don't actually
impressions.
remember how it ended up. This was on Clubhouse, which tells you roughly the time frame because it didn't last very long.
Right. Yeah, that's true.
So
it's like carbon dating. You can go back.
It's exactly. It's very, very small slice of time.
Exactly.
I don't remember how we started talking, but I do remember that we had like a 3-hour long conversation nerding out about radar imaging. And it was very technical. And I do remember walking away from that being like, this guy seems legit. Like I get to talk to a bunch of people, and even more that never make it onto the podcast. And so I talked to a bunch of people who is just crazy out of their minds. But this was not the case. And I remember us talking for quite a long time. But so that was, over 4 years ago. And you had not started, you hadn't gone through YC. YC was 2022?
2022. So almost 2 years ago now with YC. Yeah, absolutely. And so I remember a couple things about that conversation. I believe, if I'm not mistaken, that we met in the VC startup room.
It could be.
I think it was run by Michael Mealing, I think, who's a partner at Starbridge. And we were talking about SAR. And I remember my takeaway from that conversation, that 3-hour conversation, was that, it's kind of stuck with me to this day. This idea of like the founder continuum, right? And I remember that conversation. I was very much an engineer, right? There are two ends to the founder continuum. On one side is 100% engineering, and the other side is 100% like sales and marketing. And when I started Array, and even before that, when I was ideating on the idea, I was 100% an engineer. And it turns out this is not an effective strategy for long-term company growth or fundraising or anything else, right? Because you need to be able to articulate outside of the amazing technical details and technology how this is going to impact people in real life, right? And that's a little bit more of the sales and marketing side. And so my journey has been kind of towards that middle ground as time has gone on. Now, I will say, there is an opposite side, which is 100% sales and marketing. And that does not also work either, right? Because then you're like Elizabeth Holmes and Theranos, and you have to wear black turtlenecks and go to prison and talk in a weird voice. It's a huge hassle, right? And so, like, somewhere in between these two things, there's this happy medium of where founders should go and operate from. And I was not there when you and I had a conversation, because you're like, oh, how's this? How would radar work? How would this work? I'm like, yeah, sure, like 100%. These are all the answers, all these questions. Who would buy it? I don't know yet. Somebody should, though. It'll totally work. And now we have a lot better, understanding, because we talk to customers and we do all these things, and that's super useful.
There was one specific thing I remember that really stuck with me from that on the business side, which is that you told me that you thought there was some innovation on the business model aspect as well that needed to happen. Which was to go to a subscription model or to a revenue sharing model. So to say that instead of going and buying the data and then you kind of do whatever you want, you don't buy the imagery, but instead we'll take like 5% of your revenue. I'm like, change the numbers, whatever you want, but like that's the idea, so that you the Again, this is what I remember from our conversation 4 years ago, but it kind of stuck as well. It's no upfront cost. So you're also a startup. You want to go start ideas. The biggest hurdle to that is upfront money, upfront capital that you need. Why is it so hard to start a space company? Is because, well, you need to launch before you can do anything. So that's a way to like promote that guy or girl in her bedroom on a laptop to go tinker around so she can start a company. If she doesn't need to pay someone a lot of money, like hundreds of thousands to get started, that's great. So it's sort of like investing in those companies. But I remember being like, ooh, that sounds like a hard sell as well, because now you're saying you're
Yeah.
going to take part of how good I am at getting something out of this raw material that I bought from you. So let me ask you, where is this plan
Yeah, yeah,
nowadays?
yeah, 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 yeah. Like all plans that meet, have first contact with reality, changes get
But it has
made.
some merit. So like
Yeah,
I'm very
yeah,
curious
yeah,
to see like,
yeah. So, yeah, and I think the biggest part about this was if you spend enough time in the Earth observation industry, what you will realize is that different customers have different willingness to pay. Um, and so when you try to buy data from a lot of companies, you get this really interesting sales process where they try to figure out exactly how much money you're able to pay for data. Think about a mine, right, or something, something that's producing some value for a particular company who's operating it, and then like the ESG group that is interested in understanding whether that mine is being operated properly and does a good job. And not that the mine is not interested in making sure that they can operate things sustainably and within laws and whatever. But like the two different price points these companies are able to pay are like orders of magnitude away from each other. And what typically happens is the mine gets the pristine image of that location that is taken from a satellite, and then the ESG gets like the crappy imagery from a bad day or whatever it is, because they can't sell the same image to both customers, right? It has to be like 6 months old from a goofy angle on a cloudy day at low resolution with a weird, squint or whatever it is. And like, this is the product you get, right? And so you go like through these like multi-week sales process where they try to determine the maximum you can pay and the minimum quality you can accept in order to give you a product that is well balanced for your needs, right? And like this feels in a lot of ways really really stupid to me, right? If the image is sitting there, we have this image, especially as we move to what Array is going to be able to create, which is this near real time 3D map of the world, right? If the data is sitting here on our archive or in our S3 bucket, the marginal cost to serve the next customer is like data bandwidth transfer, right? Like it is not a huge expense for us to be able to give additional imagery to another customer, especially if that customer is trying to do something that's critically important, like make sure the planet sticks around and is managed responsibly, right? So like, how do we find a way to be able to right size our costs for each of these individual customers, right? Um, and there are different ways you can do that, but we try very very hard to make sure in our customer conversations that we're actually able to provide data that people are like right sized for whatever that they're trying to do and the job they're trying to perform and the value that data is going to create for that industry and for that organization, in order to make sure, especially for the long tail of small and medium sized analytics companies that are doing something niche in a particular like small domain, or not, or maybe they're nonprofits or whatever it is. They don't have a lot of money, but they should be able to have the same access to the same quality data at the same resolution, at the same or similar timescales to everyone else, because it is not an expense for us to be able to share that with them. And so that's the dream and that's the vision that we want to be able to promote. for all of these companies. Now you need to make sure that everything works well for that, right? And people aren't abusing the system or people aren't doing anything crazy. But that is really the intent behind a lot of the thoughts about what we're doing, because we're not here to maximize shareholder value, right? Like that's really really good, but we're here to build a capability and a technology that's going to be maximally useful to the largest amount of people. And it turns out if you do that, this is actually the way to maximize shareholder value, not by nickel and diming or trying to be really prescriptive to everybody who shows up. So I don't know. That's a thought that we have, and a direction that the company is going is like, yeah, if you are going to try to do something new and something innovative and something useful in the world, it should be like launching a website, right? There should be a way that is a process for you to have the same level playing field as other people around the world, for you to start and for you to start building something and creating value for lots of other people. And the easier that is, then the more people will do it and the more value will be created. And that is just a world that I would love to live in.
How do you do that in practice though? You didn't answer my question. Like, are you still going for the subscription? Like, what is? I agree. That sounds good. How do you do that in practice?
So it's a subscription for our larger customers, right? So the kind of the big blue chip technology companies that are working in AR, or the companies that are working in automotive, there's a particular price for these customers, and it is very very difficult to figure out. Okay, if Google Maps is using this data set, what is the incremental revenue that gets calculated for Google Maps by us having this thing? Like, no one knows, right? It's like it turns out a very, very hard question to answer, but we settle on a price that's negotiated between us and that customer. And that's its own transaction, and that's its own thing. And so those prices for mainline customers, large customers, or military customers, other things like that, it depends. What are you trying to do with this? How frequently would you like the data? What resolution would you like the data? Is there any additional processing that you'd like us to do to the data to make sure that it conforms to your needs, or whatever else, right? Are we detecting objects? Are we trying to figure something out for you? So that those things are more specialized, they're more one-off, and there's a different price for those customers. But yeah, for small and medium and tiny companies that are just getting started and just trying to do something, we're trying to price the data access for these customers at something like 1/10 or 1/5 of the value that this data provides to them, right? If you were gonna make $10 for us having provided you this image, please, we'll take a small fraction of what you're able to generate from this. Please take the rest of the money and grow big and strong and make lots and lots of investments in your technology and your stack to make sure that you can get all the customers that you need to, that you can make all your algorithms as good as they can possibly be. And we will be here, right? We will be here to support you with as high quality data as you can get anywhere. And so that's where we see a partnership opportunity with lots of these different companies. It's not meant to be onerous. It's not meant to be something that people are and yeah, if you want to buy the data straight off, like, for sure we can do that too. If you want to task data, sure, we can do that, right? We can do all of the other traditional models, but for people who need a little bit of help, boy, are we happy to work out a different, more flexible arrangement with them that allows them to be able to grow faster and do more in a quicker time scale.
So, you addressed this, but like I've never started a company. Well, I mean, this podcast is a business, but it's a bootstrapped business to go down that. I've never started something that would require or put myself in a place where I'd need or want to convince other people to give me money, basically to invest in. So I don't know what it's like, but you've mentioned having to go from this journey of being the engineer that's really into the technical side to becoming a founder, so basically a salesperson. And it took us an hour to be able to explain sort of how we get to what you guys are doing. And that's starting with a baseline of this industry already, and like a basic understanding of radar. How complicated or not, it is to convince people who are looking for basically a good investment that, hey, this is something that you should put your money in. Like you mentioned, hey, like we have this much amount in soft commitments, like that tends to be something that helps. But then people, if they're going to put you a multi-million check, they might do a bit of due diligence. Um, I see what you guys are doing on the sort of scale of complexity in sort of the whole Earth observation as like really getting towards it's really complicated. I watched. I had Ashley Vance on the podcast a little while. I don't know if you know who that is. He wrote
Yeah,
the first
yeah, yeah, yeah.
biography of Musk, and he came out recently with a documentary called Wild Wild Space, which follows Rocket Lab, you mentioned Electron, and Astra, so these two rocket companies, and Planet. And so most of the documentary is about these guys, what they're doing, and then there's like a good 10 minutes, which is like, we're going to explain to you why Planet is a big deal, and here's what they do. And they do like optical satellite images. They put basically a smartphone on a CubeSat, and there's 10 minutes explaining what they do. And that's the simplest company in this industry. You guys are like
Right.
even more complicated because you're doing radar and then like multi-static. Like, how much of a challenge has that been?
It's certainly a challenge, because of all the technical complexity, right? And so you need to be, and this is the failure mode of the 100% engineer, right? I will now derive for you why thou shalt make an investment in my company is not exactly a winning strategy, right? We're like nerding out about the technology for an hour before you get to the point of like why anybody would want to buy it or anything else. And so, yeah, it's definitely something that has taken a little bit of time to do, and to do reasonably effectively. Um, Kind of the strategy and kind of the thing that I look to when talking to an investor, right, is there's different categories of risk, and being able to understand what that risk looks like in these different categories and be able to articulate that well is something that's absolutely critical for those in the audience thinking about starting a company. This is the number one thing that I think that if there's anything helpful I can provide, it's looking at the world through these different risk categories, right? And there's something like, what is the science risk? What is the engineering risk? And what is the market risk for the company that you're trying to build, right? And how do you underwrite each of these different things, right? So I mentioned we had this really great idea at the beginning of YC that we're going to go build this 3D radar test range. And that was going to underwrite the science risk for the idea and say, yes, the science risk is zero. We can prove this technology. We can build a 3D simulation in a lab, in a laboratory setting, in a laboratory environment with multiple antennas. They simulate the path of satellites using commercial off-the-shelf hardware on the ground. We can build this 3D image and this 3D radar test range. And that's great. And that is valid. That was something that we did immediately after YC, right? Immediately after YC, then we built the team that could underwrite that technical science risk, and we could reduce that to zero. But more important than that was the market risk. How do you underwrite the market risk? And that's what our advisors at YC said. It was like, go make sure this market risk can be brought down to as low a point as possible, right? Now, the ultimate zero market risk company is a company that has customers who are buying the product, right? Okay, that's good. That's a really good signal. It's a really good sign. A little bit hard to do for deep tech companies that like need to launch satellites into space, but we've actually been able to do that and do that fairly well in kind of a roundabout way, which I'll describe it in a minute. And then kind of there's the engineering risk, which is like, okay, can we do the blocking and tackling and the development required to put things in space? And like and we've done that too, right? We've launched a couple satellites recently. This show, yes, we actually can do this. We can get confidence in this. Our next satellites are going to be even more sophisticated than our previous satellites, and that's going to help underwrite the engineering risk, which is actually the least important out of all of the three. Is the engineering risk, right? You need to have a market, and the science needs to work. Otherwise, there is no company and there is no hope. I do not care how good you do on the engineering execution. Okay, it's 20%, it's 200%. longer to get to market or whatever it is, like, okay, that's really important. But if there is no market, it is that is not good. That is very, very not good, right? And so, yeah, talking to customers first, that's the number one thing. I think then comes science risk and underwriting that, and then comes the engineering risk and being able to be able to pull this forward, right? And so, how do you do this? Market risk, you talk to customers, ideally, customers who want to buy something, ideally, customers who can buy something. And so, I'll actually tell you a story about something that I'm really, really excited about on the market risk perspective. It's kind of a recent development over the last couple of months. So we talk to customers and we say, do you want a 3D map of the world? And they say yes. And we say, cool, can you sign a contract to buy data from us when the satellites are in space? And they say, ah, that's a little bit hard because you're building this crazy space MRI machine that's collecting 3D data, and we have no idea what that's going to look like. But we're really excited about it. How can you give us sample imagery? Can you give us sample data? Is there something you can do? And so that was a conversation that we had over and over and over again with all of these major customers who are going to buy tens of millions of dollars worth of 3D data. It's like, okay, well, we'll see what we can do. At the same time, we were talking with a company, Raytheon. Raytheon actually was considering building a satellite constellation to collect 3D data. And we talked to them and the group and the team that was kind of responsible for this. And eventually they decided not to do it because it was going to cost a lot of money to be able to go collect this. Um, but but they were really excited about the market potential because they'd done all the market research. They realized that there was no market risk for 3D data. They really, really wanted to go do this thing. They just weren't sure about the technology, about the science, about how they could put satellites up there that could collect data. And when they saw what we were trying to do, they're like, oh my gosh, right? Like, how can we help? Is there a way? And the group we were talking to was actually responsible for creating 3D data from optical data and from other modalities. So they're a 3D creation company. And we're like, oh, can we take existing 2D radar providers? Can we give this to you? And can you turn this into 3D data? And they said, sure. And so we have a contract with them to go create 3D data on our behalf. And then we take that data to customers and we say, look, this is collected over days or weeks. This is much lower quality than anything that we're going to provide. It is much more expensive because it requires 8, 10, 20 images of the same scene to be able to be collected in order to turn into 3D data. It is worse in every way. Is this something that is helpful to you? And a lot of the customers are like, yeah, we'll wait for the real thing. It doesn't meet our needs, right? I mean, even if the quality is good enough, it's a local image, right? It's a small area that gets repeated collect. So maybe some customers need a wider area, or they need higher quality, or they need higher timeliness between all the different images, whatever they need. So some customers are like, yeah, thanks, we'll wait. Some customers are like, oh my gosh, this is really good. Like, thank you for this. We can move ahead with the contracts. We can go ahead and get some deals across the line. And that's been really helpful. And we actually have got a couple major contracts in place with some early customers who are backing the company. And then some customers were like, can we buy this? Is this like a thing that we can buy going forward? Because we've got these places in the world. There is no 3D collection that we can find to be able to capture the information that we need. Can you deploy this? Can you scale this up? Is this a product that you can launch? And we're like, I don't know, I guess. So now we have a product line. We just signed our first 100K PO for a customer who wants to pilot this data out and be able to collect things in the world. And it's low quality, and it costs a lot of money, and it's very difficult and inconvenient to collect and process and do all these things. And yet, there's still a market for this, lesser product that kind of goes again to underwriting the market risk, which is, yes, we talk to customers, they absolutely want this thing. They're even willing to put money on this thing right now and sign agreements for this data in the future. And so that's probably the most exciting piece from a market risk reduction perspective that we've seen so far. Um, Outside of just talking to them and realizing that there's a drop-in replacement for something they already use. So the market risk was already fairly low for this company to begin with, but as we keep moving forward, yeah, we keep trying to burn that down as much as we can.
How did you learn all those? I take your engineering to founder or slider. Like, how did you learn all the other skills to bring you more towards the middle of that slider? Because you're obviously really good here at explaining what you're doing, at being really excited about it in a way that someone who's spent their whole career very narrowly on their field just wouldn't be able to do. Like, you've clearly gotten very good at this. Um, and even like going through the process of like raising money and doing like, how did you realize this was a thing you needed to do, and then like what did you actually do to get better at it?
I thank you. First off, thank you. I appreciate it. It's something that um, like, what is the quickest way to get better at a thing? I don't know, trial and error. Yeah, so did it wrong for a while, and then you get a little bit better. And I think a big part, if I had to like lay credit to somewhere, would be the people who have been supportive to us in our journey. Right. So the first check into the company was from Brian McClendon, known to us as Bam, who was also on your show earlier on. He was the first person who could, he's very impressive for a number of things, right? He built Google Earth and kind of ran the geo division and Maps and Street View and all these things as one of the early founders of Keyhole. He's also very impressive because he could understand what I was trying to articulate way back in my journey as a founder when I was not nearly as good at any of these things, and he still got it, which is what it's a testament to him kind of understanding the technology so well. The second check into the company was from one of the founders of YC, Trevor Blackwell, and so and then YC was super helpful, and they gave us so much good advice that I'm still trying to use today. Go through YC if you have the opportunity. It was a wonderful experience. It was super helpful. Really, really great program that's developed and been created there. And yeah, then surround yourself with people who have kind of been there before and done it before, and listen to what they say and try your best to carry it out. But then also, be true to your own ideas as well. You got to find a balance because everybody will tell you something that's a little bit different, and you don't want to just do what the last person spoke to you. So you got to kind of like filter it and try to find the good nuggets. But yeah, I'm really grateful. This industry in particular feels very supportive and very helpful. There's a lot of folks who really want these companies to succeed. They see the value and they see the progress that can be made to the world by having better information available to more people. And so we're really lucky to have a great group of mentors and a great group of folks that can help us as we go throughout this journey to be at the right place at the right time with the right idea, focused on the right thing that gets us incrementally further to building these data sets and building these things, right? So this is a pretty cool place, I think, to be in.
One of the other things I remember from our conversation a few years ago was you. I don't know why. It's something I wrote down, but you mentioned that Star Trek had been a big influence on you, and the reason I bring this up is because I think it's a nice time to start rounding this conversation up, and
Yeah, yeah, yeah,
I
yeah.
like to ask for a book and a podcast recommendation for people. And sort of what's behind that question a lot of the time is like, what are some of the stuff that you go look at and you get influence? And that's other people, that's like science fiction. It's the stories that you listen to, it's the nonfiction stuff. We mentioned you have like Thinking Fast and Slow on the shelf behind you there. So like, I do want to ask you for like a book and a podcast, but I also want to sort of broaden it up of like, what are some of the other influences that you might have had in your journey, but in your kind of life in general as well? I'm going to purposefully leave that as a very broad question, as I've done in this interview, and I'll let you take it wherever you want.
To go back to the quote, I think at the time I said, like Star Trek, like scanning the continent for life science, right? Like this is a thing that they do. Like the away team is lost somewhere on this planet. We have no idea where. Scan the planet for the two people and the spaceship that have crash landed. And of course, the computer can do that in 18 seconds. Like, oh, they're here, right? And the plot and the story can continue. And being able to do that for the planet, man, that feels, or being able to understand what's going on worldwide, right? Like at a touch of a button, being able to see the changes that are happening all across the globe, that feels like an increase in agency for humankind. That's a world that I would love to live in terms of being able to see and react to changes. Um, in terms of book recommendations and stuff, yeah, I have a few, but the best book on sales that I ever read was called Spin Selling, and it's this really old book, from I don't know, the 70s or 80s, and it was really helpful in me trying to figure out part of this whole enterprise sales and marketing thing, and so I'll give that recommendation. Um, in other books, 0 to 1 and other books, but think people thinking fast and slow. These are all, very influential to me, but that's the nugget that I think nobody's ever heard of. That's worth taking a look at and seeing what goes on there. So that's a good book. As far as podcasts are concerned, I do have a podcast that I'm a big fan of, which is Acquired. Acquired is a great show where they go through and they talk about kind of the stories behind the formation and the strategy and the effectiveness of many of the world's most iconic companies. And every time I listen to something, I come away with something that feels really good and useful as I go about thinking about kind of how we construct Array and what kind of company and what kind of things we want to be when we grow up and get big and strong, like all these other companies. And so that's a company that's a good recommendation for folks as well.
If we talk again in 4 years, let's say we do this again, what does it look like? What does Array Labs look like, do you think?
Yeah, I'm trying to figure out how everything will change in the next 4 months, and so I don't know that I have because it's really different. 4 months ago we did. It's interesting. 4 years from now we'll have satellites in space that are collecting 3D data, and with this new architecture that is going to be so powerful, and it will. And I think at that point in time it will feel obvious that of course this is how you collect radar data. You have multiple satellites, you have multiple radars operating in concert. That's kind of what I feel will be really interesting, and I think the utility for the data products and the analytics, and the greater availability in kind of an unprecedented way will be a strong tailwind to a lot of the analytics folks and a lot of the people who are trying to get their hands on this data, but just don't have a way of being able to do that right now. So we will probably produce more 3D data than the rest of the airborne, LiDAR and photogrammetry folks worldwide combined. It would be my prediction between now and 4 years from now.
Well, I'm excited to have a conversation again by then and kind of see what we got right, what got wrong, and kind of where
Yeah.
things are by then.
Yeah, I'm looking forward to it anytime. Yeah.
Thanks so much for your time. This was a wonderful, fun, enlightening, and at times mind-blowing conversation. Thank you for kind of taking me along on the sort of thinking about what this looks like, and getting me excited about it. I feel like we can't talk for less than 2 hours every time we talk. So I'll take that as a great sign. Yeah, thank you so much for spending some of your valuable time with me. Really appreciate it.
Absolutely, Max. Thank you so much for what you do and for setting up this space where people can tune in and people can learn and people can see what's going on at different places. And thank you for being such a wonderful host and for getting all the things that we talked about and being wonderful. So yeah, thank you as well. And yeah, I also had a fantastic time. And let's do this again soon.
Hey, thank you so much for listening to this conversation. I wanted to take a moment to thank the sponsor of this video, but also all the people who financially support me on Patreon. If everything goes well, these conversations should feel and sound seamless and effortless, but there's a lot of work that goes behind the scenes. I try to research and prepare these as much as I can to know who these people are and what makes them interesting and what would lead to a good conversation. I'm incredibly thankful to all the people who support my work on Patreon, meaning I can do a little bit more of it. This podcast started out as a way to learn more about the people in this industry, but I've also started making educational content on another YouTube channel that I'll put a link to in the show notes. And I want to make more content explaining how satellite images and maps work to a broader audience, as well as continuing to research the guests for these podcast episodes. So, if you value the work that I do, I'd like to ask you to please consider supporting my work on Patreon. There's also some behind the scenes of how this podcast is done and some of the work that I'm doing for these educational videos if you want to learn more about how I do all of this. Either way, thank you so much for all of your attention and your time. I really appreciate it, and I hope you get value from these conversations. Thanks.